Welcome back, folks. Mr. Lurusso here again. We're on to video number 2 in our next unit of kinematics. And today we're going to specifically look at position versus time graphs and velocity versus time graphs. But before we get into that, I want to do a little bit of clarification again, the differences between distance and displacement and speed and velocity. So again, distance refers to the length of the path traveled. So as we move along, the distance is represented by the length of what we did here in red, and there's no direction associated with it. Whereas the displacement, that is represented by the straight line vector connecting our starting point A with our endpoint B. And velocity. Velocity is defined as the object's displacement over time, where speed is distance over time. So there's a couple of neat little things about this. So when we have a straight line, the magnitude of the displacement is going to be the same as the distance, and the magnitude of the velocity is going to be the same as the speed. But in every other circumstance, the magnitude of the displacement is always going to be smaller than the distance, and the magnitude of the velocity is always going to be smaller than the speed. And it's even more hilarious when you're going in a circle. So when you travel around a circle, this represents the distance, this red arc here. But this little short thing there, that's our displacement. So hilariously, when you complete a full circle, your displacement and your velocity are 0. What this means that every race in history that has been run around a circular track where the start line and the finish line are the same point, technically speaking, the average velocity for all of those races is 0. And the reason being is that it's displacement over time. And if the displacement is 0, then the velocity is going to be 0 as well. So that's just a little fun fact. But now let's get into it. So we're going to start interpreting position versus time graphs, or D versus T. Sometimes I will conflate accidentally, refer to distance as displacement and vice versa, because it's easy to mix up the two. But the key thing is displacement has direction where distance doesn't. But if you're going in a straight line and you don't turn back, the distance and displacement represent the same thing. But the distance, however, is the total of the path that you take, where the displacement is just from your start point to your end point. So let's take a look at this graph over here. So here at time equals 0, we're at a position of 0 meters. Now after 10 seconds, we've reached a position that is 10 meters forward. Okay, so now so far, that means we have walked 10 meters. So our distance and our displacement are the same. But when we look at from 10 seconds to 25 seconds, there's no motion. We've stayed in the same spot. So we haven't gone forward, we haven't gone backwards. So we're staying put at positive 10 meters there. We're in the same spot. So we're not changing position here. Now, let's take a look what happens when we go from 25 to 35. So we're going from a positive position of 10 to a position of negative 10. So what that means is that we have, and that's our position there. So we have traveled a total of, in this section here, 20 meters, but backwards. All right. Now, the interesting difference here, I'm just going to erase some of this. So here, in this section, we walked 10. In this section, we walked 10. And then in this section here, we walked 20, but going backwards. So from a distance perspective, the total distance that you went would be 30 meters. And the reason why is because you walked 10 forward, stopped, just kind of chilled out there for a minute, and then you walked another 10 back, and then another 10 for a grand total of 30. But our displacement does not care about what we did in between. Our displacement just looks at what happens initially and then what happened at the end. So we went from 0 to negative 10, which means that our displacement in this case is just negative 10 meters, or 10 meters back. So the distance was 30 because it counts basically all of your steps. But the displacement doesn't care about what happened in between. Just your start point, your finish point, and that's it. So in this first section, our displacement is increasing, which means that we are experiencing a positive velocity. In this time segment here, we're staying put, which means that we are at rest. We're not moving at all. Now in this time section here, we're walking backwards. So our motion is negative, but our position is still positive. So we're still ahead of our initial starting point, but we're moving backwards. At the 30-second mark, we're back to our original starting spot. And then for the next 5 seconds, we are walking still backwards at the same rate, and we reach a position of -10. So now we're moving behind our initial spot. So we now have a negative position. And then let's take a look at this here. If we just look at between 0 and 30 seconds, at the 0-second mark, we're at a position of 0. At the 30-second mark, we're at a position of 0. So 0 meters at the beginning, 0 meters here. So our displacement is 0 meters. It does not matter at all that we went forward then backwards. Displacement doesn't care what we did. It just cares about where we started and where we finished. Now there's some other interesting information about this. So let's focus on this part right here, this little segment. Well, if you take a look, we've covered a total of 10 meters in 10 seconds. If you look at these numbers, 10 meters in 10 seconds, that is equal to 1 meter every second. And 1 meter per second represents our speed or our velocity. So in this case, we are traveling in this segment here, 1 meter per second, but in the forward direction. Which brings us to our next point. The slope of a position time graph gives us velocity, specifically the average velocity. So if you take the slope along sections of a position versus time graph, it gives us the average velocity. And here's how we know. The formula for slope is delta y over delta x. So therefore, delta y in this case is the same as d. Because if you look at our graph here, our y-axis is d and our x-axis is t. So delta d over delta t, so distance over time, that is defined as our speed. So therefore, the conclusion is that the slope is equal to the velocity. And you've seen that before, although you may not realize it. But when you're on the highway, specifically the 400 series highway, the speed limit is 100 kilometers per hour. My goodness, could you imagine if it was 400 kilometers per hour? 100 kilometers per hour. If you look at the units, that's distance or displacement sometimes, and that's time. So speed is equal to our distance over time, whereas our velocity would be our displacement over time. So let's do an example, and we're going to analyze these things here. Okay, so starting off, at a time of 0 seconds, we're at a position 0. So that's right there. So now we go to the 10-second mark right there, and up to 15 meters. That's that point right there. Then at the 30-second mark, which is over here, we're at a position of 15 meters again. Then at the 45-second mark, we're at a position of 0. So right there. Now let's take a look at 60 seconds. We're at -15. So that's right there. At 80 seconds, we're at -15. And then at 90 seconds, we're at a position of 0. So at 90 seconds, position is 0. And now we're going to connect the dots. And it's going to look a little something like this. So the next step, what we need to do is we need to calculate the displacement and average velocity for the following time intervals. So between 0 and 10 seconds, 10 and 20, 30 and 45, 80 and 90. So focusing on our first segment, we're going from 0 seconds to 10 seconds. So it's this little segment right here. So from 0 to 10. So our initial time is 0, our final time is 10, and our initial position is 0, and our final position is 15. So to calculate our displacement, that's equal to our final position minus our initial position. Now technically, that's a delta, but hear me out. We physics folks don't always put the delta in. I know, it's a bad habit, but the issue is having to write delta every single time is mind-numbing, especially when you have so many calculations to do. But in any case, we'll get more into that when we kind of cheat and drop it. Now, I'm just going to use positive and negative because we don't really know which directions these are. Technically, forward and backwards would be your default, but our final position, positive 15 meters, where our initial position was 0. So therefore, our displacement in this section is 15 meters forward. Finding the average velocity, that's just your displacement over time, which works out to positive 1.5 meters per second or 1.5 meters per second forward. Next, let's focus on the next time interval. That's between 10 seconds and 20 seconds. So that is this segment right here. Well, the displacement is the change in position, and our initial and final position, they're both at 15 meters forward. Our initial, our final position. In both cases, we're at 15. So our displacement is 0 meters. We didn't go anywhere. We're at rest. Now, you'll notice I have a harpoon over top of the 0. That is our notation for what we call the 0 vector. All vectors have to have a direction, but 0 is omnidirectional. You literally can go nowhere in every direction. So instead of committing to a specific direction, we just put the harpoon over top of the 0, and that indicates every direction. And since the displacement is 0, our velocity is also going to be 0, and of course expressed as a vector. Between 0 now and 45. So our displacement in this section is 0 minus positive 15, because at the end of the segment, we're at 0, and at the beginning of the segment, we're at positive 15. So our displacement is negative, which means we've moved backwards. Calculating the velocity, negative 15 divided by 15, which gives us 1 meter per second backwards. Between 80 and 90 seconds now. Our initial position is negative 15. Our final position is 0. So again, our change in position is d2 minus d1, 0 minus negative 15, and that works out to positive 15 meters, or 15 meters forward. Calculating our velocity, that works out to positive 1.5 meters per second, or as a vector, 1.5 meters per second forward. Now let's focus what happens when we have a larger segment between 0 and 30 seconds. All right, now things are a little bit different. And since we're talking about displacement, we don't care about the path. So what we got going on here is that's our initial position. And let's go to 30 seconds. We're over here. So we're basically worried about this blue line here, not what actually happened during that interval. We don't care that we're only moving for part of it. The average is represented by this blue line. So again, our initial position, 0 meters, final position, 15. So our displacement is just 15 meters forward. But where things get different is with the average velocity, because now our time interval is bigger. So this works out to positive 0.5 meters per second, or 0.5 meters per second forward. All right, so let's look at the next interval. So now we're going down to 45 seconds. So let's redraw our blue line. It's looking pretty flat there, and for good reason. So now, in this segment, our final position and our initial position are both 0. So that means our displacement is just 0 meters. And no shock, our average velocity, 0 meters per second. Next, 0 to 80 seconds. So moving our final position to the 80-second mark, readjusting our line here. Now you can see that it's sloping down a bit. So that means our final position is negative 15, and our initial position is 0. So in this case, our displacement ends up being negative 15 meters or 15 meters back. And this also gives us an average velocity of 0.1875 meters per second backwards. And again, it doesn't matter what we did in between. All that matters is the difference between the final and the initial position and how long that took. And finally, between 0 seconds and 90 seconds. So our final position at 90 seconds is back to 0 again. And as you can see, we got another horizontal line. So we end up getting a displacement of 0 meters again, and an average velocity of 0 meters per second. So now on to part C. During which intervals are the velocity and displacement equal to 0? Well, we already identified a few of them, 10 to 20 seconds, 0 to 45, 0 to 90 seconds, but in fact, there are a lot more. It's basically this. If you take a line and cross anywhere and find a flat spot, that segment, the average velocity is going to be 0, and the displacement. So number 1, we got that there. Also, there, tighten that up a bit, there, that whole segment, this segment here, all of these represent a displacement of 0 and an average velocity of 0. But actually, just any horizontal line between there and there, it's the same thing. So there's actually a bunch of solutions, but the main ones are the obvious ones that we just pointed. And then the final question, predict what the velocity and the position would be at the 100-second mark. So we got to figure out what's going on here. Easiest way to do it is just continue the line. And if you continue the line, the prediction should be this. At the 100-second mark, you should reach a position of positive 15 meters. And that's just following the trend with the last segment of motion.